Hi, I'm Shahnawaz. In this lecture, we are going to study the local rings. There are rings with exactly one maximal ideals, and such rings are called the local rings. For example, if we look at a field which is a ring, so in these rings, 0 is the only maximal ideal. So any field is a local ring. So let us define these rings. So let A be a local ring, let A be a ring, and let A be any ring. So if A has exactly one maximal ideal, say M, then A is called a local ring. Now this M being a maximal ideal in A, so the quotient A mod M will be a field. The field A mod M is called the residue field of A. So this is the definition of a local ring. Now we have this proposition. So it has two items. So the item first is let A be a ring and M be a non-unital ideal in A such that every element which is inside A but not inside the M, I mean an element inside the set A minus M is a unit. Then M is the only maximal ideal in A, that is A is local. Now we have item second here. So let A be a ring and M is a maximal ideal. In A such that every element of the form 1 plus M, where M is in M is a unit, in A, then A is again local. And in this case this m will be its only maximal ideal. So let us prove the item first. Now let us pick any element. Now this set A minus m is like this, so this is the set A here, and this is the ideal m. Since m is non-unital, it cannot be whole A, and this is the set, and this is the set A minus m. So any element in this set, I mean an element which is in A but not in M, is given to be a unit. That means all non-units in A are inside M, i.e. M contains all non-units in A. So we are just picking an element in A minus M. So let X be an element of the set A minus M. So therefore, now this X is not inside M, and M is, or let us do this way. Let us do this way. So let I be any ideal which is non-unital, be any ideal in A. Now this I being a non-unital ideal means the only element is in I are the non-unitals. Therefore I consists of non-unitals in A. I consists of the non-unitals in A, but all non-unitals in A are inside M. That means this I is contained in M. Hence I is contained in M, since all the non-unitals are inside M. So this is true for any non-unital ideal. That means this M is the only maximal ideal. Hence M is the only maximal ideal in A. So this proves A is local. Hence A is local. Now let us prove item second. So this is the proof of, this was the proof of item first. Now let us prove the item second. Now in item second we are given M to be the maximal ideal. Now what we have to prove? We have to prove A has just A has exactly one maximal ideal, that is the M itself. Now what we are going to prove? We are going to use item first to prove our claim in the item second. I mean we prove every element inside the set A minus M is a unit. So that is what we are going to prove. So let X belongs to the set A minus M. I mean an element which is inside M and outside, inside A and outside M. Now this M is given to be a maximal ideal. So M is given to be a maximal ideal. Now if we look at the ideal which is generated by the elements of M and the element X. Now since this X is outside M, so this ideal will contain properly M. But M being a maximal ideal, that means this ideal is actually the unital ideal, i.e. the ring itself. So if this X is outside M and M being maximal, therefore the ideal generated by X and M. Now by M means by M we mean here that the elements of M, the idle generated by X and the elements of M is the unital ideal, since M is maximal and X idle generated by X and M contain M properly. So that is why this has to be unital. That is, the ideal X and the idle generated by X and the elements of M is actually the unital ideal 1. So that means there is some element in this ideal which is actually equal to 1. So therefore there exists, say, y in A such that this xy plus t is equal to 1, where t is just an element of M. That is, this xy is actually 1 minus t. Now in second we are given this condition that every element of the form 1 plus m, where this m is in this big M, is a unit. So if we look at this element here, so this is of the form 1 plus m, where m is minus t. So this has to be a unit by hypothesis. Therefore by hypothesis, this 1 minus t and hence xy has to be a unit. Xy is a unit in A. Thus there exists z inside A such that xy times z is 1, or x times yz is 1, since the multiplication in the ring is associative. So this means x is a unit. Therefore x is also a unit in A. So this x was chosen arbitrarily inside A minus m. That means every element in this set is unit. So therefore by item first, m is the only maximal ideal in A. Hence by item first, m is the only maximal ideal in A, i.e. A is local. Now there is this fact that in a commutative ring with the identity element, every maximal ideal is a prime ideal. This follows from the fact we know that if A is a ring and M is a maximal ideal in A, then M is maximal if and only if A mod M is a field. Now suppose this is a field, that means this is also an integral domain. So if this is a field, that means this A mod M is also an integral domain. So this would imply M is prime as well. So that means in commutative rings with unity, every maximal idle is prime idle, but this is not the case in the reverse direction. I mean, every prime idle need not be a maximal idle. For example, if we look at the ring of integers, so the idle 0 here is a prime idle but not a maximal idle, since this idle is properly contained in the ideal generated by 2. Now if we look at the principal idle domains, which we have not defined yet, in such rings every prime idle is a maximal ideal. But for that we'll first define the principal ideal. So we have this definition here. So if let A be a ring and I be an ideal in A, then I is called principal ideal if I is generated by a single element, that is, this I is actually an idle generated by some element, say x, where this x is in A. A ring whose only idles are principal idle is called a principal idle domain. So a ring whose only ideals are principal ideals, whose only ideals are principal ideals, is called a principal ideal domain. And as a shorthand we write PID for principal ideal domains. So let us have an example. So if we look at the ring Z of integers, so the only ideals in Z are the principal ideals. So since every ideal I in Z is of the form ideal generated by M for some non-negative integer M, that is a PID. So this is an example. Also, if we look, if K is any field and we look at the polynomial ring in one variable, say X, so this is a field, sorry, this is a PID. So the condition is that K has to be a field. So this is a PID where K is a field. So these are some examples. Now let us prove the fact that every prime ideal inside a principal ideal domain is a maximal ideal. So let us prove this. Let us prove this. So let A be a PID, I mean the principal ideal domain. So any ideal here will be a principal ideal, i.e. the ideal generated by one element. So let X be any ideal in A. So suppose P is, this ideal is a prime ideal. Suppose this is a prime ideal. Now what we have to prove? We have to prove this is a maximal ideal. So if this is a maximal ideal, there is nothing to prove. Now let us suppose there is some ideal, say ideal generated by Y, which properly contains X. So then we have to prove this ideal Y is actually the unital ideal. So let Y be any ideal such that this Y contains properly X. So to prove this is maximal ideal, I mean the ideal generated by X is maximal, we have to prove this ideal is unital ideal. So this implies X is an element of the ideal generated by Y, because this is lying inside this ideal, or this means this X is equal to Y times some element of A, say Z, where Z is inside A. Now we know that this X is inside the ideal X, but this X is equal to YZ. So that means this YZ is inside X. So this further implies that YZ is inside the ideal generated by X. So now we are going to use here the fact that this ideal is a prime ideal. So one should note here, since this containment is proper containment, that means Y cannot be an element here inside the ideal X. So Y cannot be an element there. So since YZ is there, it follows Z is there, because this ideal is prime ideal. So if the product is there, one of them has to be inside the ideal. So suppose and this ideal is not prime ideal, so it is not necessary that one of them should be there, but it is given that this ideal is prime ideal and Y is not there, so it follows that Z is inside there. So since Y is not inside the ideal, so this follows from this fact, because this containment is proper, and X being prime, we have Z is inside the ideal generated by X. This implies so this implies this Z is X times some element of A, suppose T, where T is, or let us write this as xt, because the ring is commutative, this won't matter. So this is T times X, where this T is inside A. So now this X is same as YZ here, and this YZ is same as Y times Z, that is TX. So using the right cancellation law, we have yt is actually the identity element 1. So that means y is a unit. So this implies now y being a unit, so this ideal will be a unital ideal. So this implies the ideal generated by y is actually the unital ideal 1. So therefore the ideal x is maximal. Now there is this question. So we have mentioned earlier that the ring, polynomial ring in one variable, this is actually a PID. So if we look if we will cook up a homomorphism phi from kx to k by sending the polynomials and their constant terms. So this phi is defined as, so p takes the polynomial fx and it maps this polynomial to the element f0, which is some constant in k. So one can note here this is a ring homomorphism with the not just a ring homomorphism but also a surjective ring homomorphism. Now if we look at the kernel of this homomorphism, I mean if we look at this ideal here, so this is all those polynomials in kx such that f of 0 is actually 0. I mean phi of f is 0, which is same as all those ideals such that phi of f is f of 0 is 0. Now this is the set of all those polynomials whose constant term is 0. So in a previous lecture we have mentioned that this is an ideal because this is also a kernel here. So this is an ideal here in kx. Now invoking the first isomorphism theorem, and now this phi being surjective, we know that this kx mod the kernel of this homomorphism, which turns out to be the ideal. Which turns out to be the ideal whose constant terms are 0. I mean the ideal which consists the elements of kx whose constant term is 0. So this is actually isomorphic to k. Now this k is a field, that means this kernel phi is maximal here. So it is also a prime ideal here.